When we talk about gases and we talk about gas laws, first thing you want to remember is that they are empirically derived. Empirically derived, meaning we're talking by experimentation. Okay? They figured it out by experiment. And what they looked at is they looked at the basic variables of a gas: pressure, volume, temperature, and then the amount of gas. And by varying these variables and by discovering the relationships between them, we derived all of the gas laws that we're going to talk about. Now, quick reminder, when we talk Boyles Law, the main thing to remember about Boyles Law is it is the relationship between pressure and volume. Notice that pressure and volume are inversely proportional, and notice that temperature is constant. Okay? Temperature is constant, which basically means temperature has no impact. The other thing that's assumed is also this idea of a fixed quantity of gas. So the fixed quantity is constant. So go back to our things. We're looking at pressure, volume, temperature, and amount of gas. These guys are held constant. They don't change. That means we've just isolated pressure and volume, and we discover they're inversely proportional. So it's like looking at a balloon. Okay? If I apply a lot of pressure to this balloon, I can compress the gas in the balloon. But if I loosen up the pressure on the balloon, I'm going to see this balloon expand. So we have an inverse relationship between pressure and volume. Now, what this means in terms of graphing is that when we plot it, pressure versus volume gives us a very nice curve. In other words, I can look at this and I can see that increasing pressure causes decreasing volume. If I see decreasing pressure, I see increasing volume. So we get that inverse proportion. Now, what's interesting here is our K. So our K is, in essence, a constant. What we do is we say, okay, we know that pressure and volume is always going to behave the same, so we have this constant in here that it always equals to. So as I change things, it's always going to equal a constant. It's a constant number. What's important about this is what allows the algebraic formula that we looked at with the lab that we did, the Boyles Law lab, is that my initial pressure and my initial volume, since they equal a K, that means my new pressure and my new volume must also equal the same K, hence P1V1 equals P2V2, because this is a constant, and a constant, like anything, is unchanging. All right, so let's watch the video.
When the gas in this cylinder is compressed at constant temperature, the gas pressure increases as the volume decreases. Robert Boyle, experimenting with air, found that the product of the pressure times the volume is a constant at constant temperature. Dividing through by the pressure, we see that volume is linearly related to the reciprocal of the pressure. These pressure-volume relationships are expressed by Boyles Law.
Okay, and that's all we're looking at when we talk about Boyles Law. Okay, so that brings us to the next one, Charles's Law. Now, the main thing to remember about Charles's Law is that Charles's Law is looking at now volume and temperature. And we already know this a little bit because if you've had any experience with hot air balloons, you know that increasing the temperature on an amount of gas causes the volume to increase. That's how the hot air balloons go from on the ground to becoming lighter than air. We change the density, etc. So what's interesting though about Charles's Law is it is this extrapolation right here. This extrapolation is what allowed us to figure out absolute zero Kelvin. So it was an extrapolation of Charles's Law. But again, we have that same constant. So at constant pressure, at constant amount of gas, a fixed volume of gas, we see a direct relationship between volume and temperature. Now, what's important and cool about this is we can combine these. If I know that volume is proportional to the inverse of pressure, and I know volume is proportional to temperature, volume is therefore proportional to temperature over pressure. Okay, I get a single expression. So notice what we've done is we've simply taken the equations, our constants, okay, our constant equations, and we've combined them into a single expression, a single relationship. This is what's known as combined gas law. Now, when we combine them into a single expression, combined gas law is also how we can explain our little balloon here being compressed in ice and expanding in warmth. Okay, pressure changes, volume changes, temperature changes, and so we get a relationship. And we have what's known as the combined gas law expression. And again, just like before, since they equal a constant, I've rearranged this into a single thing, so that means literally I know that Vp over T is going to equal that same constant that we've been equaling. And now, if it equals a constant in one situation, it's going to equal a constant in another situation. So think of this as initial, think of this as final, and so they're equal to each other. And that's combined gas law. Now, the next one is, Avogadros. Now, Avogadros is when we finally bring in amount. Okay? We finally bring in the amount of gas. So in other words, how much we have. Now, what's cool is Avogadros Law, this right here, figuring this out, this volume and amount of gas, is behind the mole. This is actually where we get Avogadros' number, is from Avogadros' work with gases. So if my volume is proportional to the amount of gas, that means changing my amount changes my volume. Well, it's from this that we get the relationship of 22.4 liters of gas equaling 1 mole of a gas. Now, this is at particular conditions. This is at STP, which you should remember from the previous notes, standard temperature and pressure. But this is where we get this. And so if I have 22.4 liters, I have a set volume, I have a set temperature, I have a set pressure. To occupy the same amount of space, I have to have the same amount, literally the same number of particles. Therefore, that's where we get Avogadros' number. Now, all of this, what's really cool too about Avogadros, let me pause real quick, is when we talk about Avogadros' number, it's also inherent in our stoic and our balanced equations. In other words, 2 liters of hydrogen to 1 liter of oxygen gives me 2 liters of water, okay, when we're dealing with gases. And so it's a very nice literal interpretation as well. Now, when we deal with the ideal gas law, which is ultimately the point, it's the combination of all of these. And by the way, there's one gas law we're not going to spend a lot of time on that you probably want to look up, is Guy-Lussac. And he is basically pressure temperature. The proportion between, well, that's a terrible proportion sign, but we're looking at pressure and temperature, but you can figure out from here. In any case, when we combine these, we get the volume is proportional to the amount of gas, the temperature, and the pressure. Well, that also means when we talk about the amount of gas and we're dealing with the ideal gas law, we have to deal now with our constant. Okay, what's really cool about our constant is notice the units. The units are crucial to understanding our R value, okay, in our ideal gas law equation. Notice how the numbers change. I go from 0.08 to 8.3 to 1.9 to 8.3 to 62. What I want to point out is notice what's constant, okay? I have mole Kelvin, mole Kelvin, mole Kelvin, mole Kelvin, mole Kelvin, okay? Those are all the same. Notice what's really changing is here I have atmospheres, I have pascals, I have torr. Now I'm not going to deal with the volume yet because typically we're going to be dealing with, most of the time what we're going to be dealing with is 22.4 liters. Okay, so calories and joules, that's another way to use it. We're not really going to be messing with those, so we're going to kind of ignore those. But the main thing here is notice that torr, pascals, atmospheres, especially here, liter atmospheres, liter torr, the difference in this number is strictly due to the unit of pressure. So the thing I want you to recognize is that it's the unit of pressure that is determining the value of R. Okay? So that when we look at the ideal gas equation, since I know that V is proportional to these things, and so V therefore equals R times these things, this is my new expression. Okay? Depending on the class, you'll hear this termed pivnert, pervnert, pervert. However you need to remember it, that's the thing you need to recognize is you need to do this. Now, what we will typically deal with when we're looking at these things, since I told you that pressure, the unit of pressure is what determines it, volume, 22.4 liters, 1 mole of gas at 0 degrees Celsius, which by the way, 273 Kelvin. Whenever we deal with gas laws, we always put it in Kelvin Always, 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 because 0 degrees, you can't multiply by a 0 and get anything other than 0, right? Mathematically, this is why we had to develop.
Michelle Campbell, please come to the attendance office. Michelle Campbell, please come to the...
Okay, so this is why we have to, this is partly why we got an absolute 0 with Kelvin, and that's partly why Kelvin was developed. In any case, 0 degrees Celsius, 273 Kelvin, 1 mole, and our and then, so we have volume, amount, and temperature. So that means pressure is what changes it. Well, remember that 1 atmosphere is the same thing as 760 millimeters of mercury, which is the same thing as 101.3, oops, I ran out of room, kilopascals. So therefore, depending on which one of these numbers we plug in, okay, whether we plug in the 101.3, the 760, or the 1, that's going to change my value of R. Because I can rearrange this so that I know that R equals, okay, PV over NT. So you can always solve for R, but you need to recognize that as we go through this. Now, when we look at then Dalton's law of partial pressure, so this is the next law that we're going to deal with. The main thing here is to recognize that all gases fill their containers. If all gases fill their containers, that means no matter what gas I have, if we look at tires, or we look at a barrel, or we look at an aerosol can, whatever gas is in there is completely filling its space. It doesn't matter what's happening. If I take a tire and I fill it with gas, okay, and then a little while later I fill it with more gas, okay, the pressure is literally a result of all the gas I've added. So literally P1, P2, P3. It doesn't matter what the gases are. That's what creates my total pressure. So pressure is based on the gases that are involved. So partial pressures, the reason we care about this is the next lab we're going to be doing, deals with collecting a gas over water. Well, that means that the pressure is going to be a result of both the water vapor and the actual gas we collected. And so that's real important to recognize that total pressure is comprised of all the gases. So when we look at atmospheric pressure, for example, we are looking at air. We're looking at nitrogen, carbon dioxide, oxygen. We're looking at the impact of all of those gases. Now, the last thing we're going to talk about is effusion. Effusion and diffusion are defined by Graham's law. In essence, effusion, basic definition, just know we have a little tiny hole and it escapes. It's kind of like opening the end of a balloon. So, basic definition, effusion, we're just trying to escape a hole, like I said, the balloon through the thing. Okay, so when we talk about effusion, what's interesting, rates of effusion, in other words, okay, keep in mind a rate, we're talking about how fast something happens, is different for helium versus nitrogen. And that difference, if we look at helium and nitrogen, well, we know helium is actually a lighter gas than nitrogen, so it actually moves faster. Now, this is the same thing that's related with diffusion. Since you already know diffusion, you should know this from previous classes, biology, everything. It's literally how fast something spreads. It's sort of like if I look at, we've talked about diffusion rates. If you put a little bit of food coloring, if I dribble some food coloring in here, we know after a while the food coloring spreads throughout and it diffuses. Okay, it turns out the diffusion of gases and effusion of gases are related to their speed, okay, their kinetic energy is, remember kinetic energy, and this is from like physical science, mass times velocity squared. So 1/2 mass times velocity squared. Well, if they're at the same temperature, okay, so we know, you should remember this equation from previous classes. Now, the big thing here that I want you to remember is when we talk about kinetic energy, remember from what we just got through finished doing, kinetic energy is the average kinetic energy is what we know as its temperature. So if I have two gases at the same temperature, that means they have the same kinetic energy. That means this has to be the same. So that means their mass and their velocity are proportional. In other words, the heavier the gas, let's go back to our demo here, the heavier the gas, the slower the rate of effusion, the slower the rate of diffusion. So what happens is we have this relationship, this ratio that occurs, so that with greater mass, increasing mass, I have to have lower velocity to maintain the same kinetic energy. Okay?